last class we were talking about, if you remember, we were talking about Mises criteria. We called this, as I told you in the last class, as a failure criteria in the earlier classes, and actually they are yield criteria and so on. We had come to a stage where we said that we will find out what this k is. We said that the Mises criteria or the yield function is such that it can be written in terms of J2, and hence we call this as J2 flow theory, and said that J2 is equal to k squared. So, we said that our main aim is to find out what this k is. That is where we stopped in the last class. We also said that we can get that k from a uniaxial specimen. So, when I conduct a uniaxial test, then the stress tensor can be written in this fashion, that sigma 0 0 0 0 0 0 0 0 signifies what we call as the stress tensor. Please note that this has to be split into a hydrostatic part and the deviatoric part. Okay, we said we call this as additive decomposition, and the pressure P is determined by 1/3 the trace of this matrix, which happens to be sigma in this case. So, P is equal to sigma by 3. Okay. From this we can write down the S matrix straight away by subtracting P from sigma. That is where we stopped the last class, right. And now writing that down, S is equal to sigma minus sigma by 3, 0 0 0 minus sigma by 3, 0 0 0 minus sigma by 3. So, what is the next step? The next step for me is to find out what is J2. What is J2? Half Sij Sij. Remember that there is a summation on I and j. So, in this case what happens to this Sij? It is just half into S11 squared plus S22 squared plus S33 squared, because others are 0. Okay. So, that happens to be, what is it? That happens to be, this is 2 by 3 sigma. So, 4 by 9 sigma squared plus second term 1/3. So, 1 by 9 sigma squared plus 1 by 9 sigma squared, right. So, and that happens to be 1 by 3 sigma squared, 6 by 9 into 1 by 2 and so on. Okay. We will stop for a moment here and get back to my previous stress tensor. We very well know that yielding occurs in a uniaxial case when sigma reaches sigma y, or in other words the critical sigma in a uniaxial tension is sigma y. So, in other words I have to put here to get my critical k, or the k which is of interest to me, by substituting for sigma as sigma y, right. So, I put here sigma y's, okay, and hence I get J2 to be sigma y squared by 3. What should that be equal to? K squared, and hence K is equal to sigma y by root 3. So, now I can rewrite rather my Mises equation as J2 is equal to, or root J2 is equal to, what happens? Sigma y by root 3, that means sigma y by root 3, and what is root J2? That is half Sij Sij is equal to sigma y by root 3, just bringing that root 3 the other side, I can write this equation as 3 by 2 Sij is equal to sigma y. Right? Now, I have a combination of the stresses, okay, which can be compared directly with sigma y, okay, or in other words I get one number from these 6 numbers to compare it with the material property called sigma y, and hence I call this whatever is inside this or whatever the root symbol or whatever is in the left as sigma E equivalent, because it is equivalent to a uniaxial stress, equivalent or Mises stress and so on. So, equivalent stress also means it is the same as Mises stress. Hence, in a 3-dimensional case I calculate this value, compare it with sigma y and tell you whether there is going to be yielding or not. Okay, and that is what we have been seeing in all our earlier work or slides. Okay, is there any questions? Right. Now we move over to another quantity called strain. I have a very similar problem again when I look at the strain, because in your earlier classes you would have defined strain on the basis of change in length by original length. Okay. So, probably the only thing you would have studied or you would have known is that if I take a bar whose length is L, and you would have said that if delta L is the change in length of this bar, okay, then delta L by L you would have defined as epsilon. Please remember that in our earlier discussions on stress, we retained the fundamental definition of stress, but made it more rigorous by taking a point, a plane and so on, right. That is what we did. We will do exactly similar things when we define now what is called as strain. Why is that becomes important? Because I have a body where the strain distribution can be different. So, what is length? There is no length to a 3-dimensional body. I can't define a length to it, okay, and I can't define a change in length to it, and hence my definitions have to be very precise when I go to a 3-dimensional situation. No doubt I will use this kind of relationship, but it would vary as you are going to see now. Okay? We will get back to the definition of strain now. Let us put a body, okay, let me say that there is some coordinate system for this body. Okay. Now, this body, let us say after application of load, okay, is displaced in this fashion. Okay. We will come to this in a minute, what this means and so on. Let us complete the definition of our problem. Let us say that I am watching this point P, okay, but since our definition of strain just now says that we are interested in change in length by original length, okay, let me take another point Q, okay, which is very close to this P, okay, and look at this line element, okay, which is joined by PQ. Both of them are very close, okay, infinitesimally close. Let us now watch this line element and see what happens to this line element, right. Let us say after deformation this body goes to this position. There is usually a confusion between displacement and deformation. Okay. Now, let us try to understand a bit, and this is only a nicety, people may not follow it so very closely. When this body, I have a duster for example, okay. this duster is just displaced and kept here. Okay? It is just displaced and kept here. Is there a strain in the duster? No, because this is a rigid body movement as it goes to this place. It is just a rigid body motion. As a body, as a rigid body, it is not deforming. As a rigid body, it moves from one place to the other place. Okay? On the other hand, I have a duster and start pulling it. Okay? As I pull it, definitely there is going to be a deformation to the body. Okay? And this deformation is what causes strain. This is intuitive to you. What do you mean by deformation actually? What do you mean by, what do you understand by deformation? You understood these two terms. I displaced it, I deformed it. Yeah, in other words, there is a relative displacement, or in other words, the displacements are not uniform throughout the material particles of the body. Yes, they are also displaced from one position to the another position, right? When I pull it, there are some particles which has moved, right? But the movement of these particles may not be uniform. When I do all sorts of things to this duster, the movement of these particles are not uniform. So this non-uniformity of displacement is what you would have intuitively called as deformation. It's deformed. Okay? And we know that this is what causes strain. In other words, if the displacement of P and Q has to be the same to another point, say small p and small q, okay, and this displacement vector is called by, say, a vector u, and if this q also happens to go to this q by the same displacement vector, then there won't be any strain. Is that clear? So that is what is going to cause, or that is what is going to be our basis for further definition of our strain. Let me say that, look at this carefully, let me say that I put a coordinate system for this deformed body. Okay? The coordinate system need not be x1, x2 and x3. Let me call this coordinate system as, say, psi1, psi2 and psi3. Do not worry about it, but just say that my coordinate system can be psi1, psi2, psi3. What does it mean? It means that this P which has a coordinate, say x1, x2 and x3, now after application of loads, load, boundary condition, whatever it is, okay, at the end when the fellow reaches, say, equilibrium, okay, has a coordinate which is given by psi1, psi2 and psi3. Is that clear? They can be related by a vector, say u, and q and p, q and the small q can be related by another vector, say u plus du. Okay, this, in other words, q is moved to the small q through another vector u plus du. This is what we have been harping on. Du has to be present. Is that clear? If du is absent, then there is no strain, nothing happens. So u varies in this whole geometry. Is that clear? Okay. Now let us say that we can write down the coordinates of the new, or the position of the body, or the deformed body, okay, in terms of x1, x2 and x3. So let us say that, note this carefully, this is going to be slightly confusing, but I will just explain that. Psi I is equal to psi I x1, x2, x3. It is customary in your earlier classes to have written this as some function of, you will write like this, okay, and if you want to write u also, you would write, say, ui as some function of x1, x2 and x3 and so on. Now there will always be a confusion between this function and this function. So you will keep on putting f1, f2, f3, f4 and so on. So that is much more confusing. Okay. So please note, in solid mechanics this function symbol is replaced by what is there in the left hand side itself and is given like this. What does it mean? It means that it is a function of, it's a function of x1, x2, x3. This psi I is a function of x1, x2 and x3. Is that clear? Okay. Or in other words, what it means is, instead of saying psi 1 is equal to say f1 x1, x2, x3, psi 2 is equal to f2 x2, x1, x2, x3, psi 3 is equal to f3 x1, x2, x3, and u1 is equal to f4, and so on and so forth. Keep on writing like that. That's very much confusing. After some time, you will not know f4 is what. Instead of that, if I write say psi 1 is equal to psi 1 x1, x2 and x3 instead of f1, I will know exactly what this function is. I can write down this as a, say I can say this is 2x1 plus 3x2 squared plus 4x3, something like that. That's a function. Okay. So what is this function? This function is for say psi 1. For psi 2, I can just have psi 2 is equal to x2. That's another function. Is that clear? So in order that I distinguish between f1, f2, f3, f4 and so on, I write this as psi 1 is equal to psi 1 x1, x2, x3. So this is, you understand this? This is a symbol for function. Is it clear? Any doubts? Okay. So this is what we are going to follow throughout. This is what most of the solid mechanics textbooks would follow. Both the symbols would be the same. So here also we will put ui. Okay. Now, what is this, or what is it that I have to get? I have to find out what is the change in length. I don't want to leave my tradition. I do not want to leave my tradition. I still want to keep my tradition there. So I have to find out change in length, okay, and hence I have to find out what is the length of the original line segment capital P capital Q and the new line segment small p and small q, right. Okay. Let me write down capital P capital Q, that is the original line segment which is here, the length of it to be square of its length rather to be ds squared. Is it clear? That is the square of its length. Now what is ds squared? What is ds squared? Can you tell from this? How do I find out ds squared? Okay, it's very simple. Suppose I call, so I have to define one more. Correct, that's exactly what I am coming to. So suppose P is equal to x1, x2, x3, Q is equal to x1 plus dx1, x2 plus dx2, x3 plus dx3, because this Q is very, very close to P, and hence ds squared is nothing but dx1 squared plus dx2 squared plus dx3 squared. That's very good, and hence that can be written as in our new found symbol, it is written as dxi dxi. Is that clear? Okay. Now let us call this guy small p small q length as ds squared, right. That ds squared is now d psi I d psi I, and that I am going to write it as say delta ij d psi I, excuse me, d psi I d psi j. Okay, is that clear? Now my question is, how do I find out d psi I? How do I find out d psi I? Let us see whether you understand whatever we have said now. D psi I, get back to this figure. I said that this is u, this will be u plus delta u. So let me say that u plus say du vector, I mean of course. So, what will be d psi I? So, I am now tracing q, right. So, that will be if there is nothing, if there is no change or there is du is equal to 0, what will happen? What will be qi? What will be the position of q, small q? Same. So, what do I write here? Oh, dxi, very good. So, the position will be the same. Okay. Now, on top of it I have added du. Okay. So, plus dui. What is dui? Look at this. Dou ui by chain rolling, dou ui by dou xj into dxj. Okay. This comes out from this expression. Okay. So, this is dui. Is it clear? Okay. Now, let me write this dxi as delta ij dxj. I just write it because I want to take that dxj out. So, and write d psi I, that is equal to delta ij plus ui comma j dxj. Right? Is that clear? Any questions? Okay. Now, what I am going to do is to substitute this into ds squared, this equation, small ds squared, that equation which is sitting there. Now, that is going to result in a slightly more complex indical notation situation, which I am not going to do it, and I leave it as an exercise because that is an excellent exercise for a student to do. So, I am not going to, what I am saying is you just substitute it here in this equation and see what you get and compare it with the result what I am going to write now. Okay, I am not going to do that substitution, nothing great, nothing, no big concept that is involved. Only thing is that here you have to systematically write the indical notation, and that will be a very good thing to write, and that will be your first problem for tutorial. How are you going to get the result which I am going to write now? Okay, let me write that result. Maybe I will remove this, let me keep that part. Okay, and hence I am going to write ds squared delta ij, ds squared is equal to delta ij plus ui comma j plus uj comma I. Note this carefully, comma you know, I hope you remember, dou ui by dou xj plus, okay, let me remove that also. U k comma I, U k comma j dxi dxj. See, note this carefully, k comma I, k comma j. Okay. Now, this term means that there is a summation in k, obviously you know that. Is it clear? I hope all of you remember what is d capital S squared. What is d capital S squared? dxi dxi, which is delta ij dxi dxj. So, that is the first term. Okay. Now, let me note this carefully. Let me define a strain tensor. Let me define a strain tensor which is given by ds squared minus ds squared is equal to 2 Eij dxi dxj. And call this as what is the strain tensor? E, and call this as Green strain tensor. Is it clear? Okay. Now, we will come to this explanations of this and see how best we can relate it to our earlier lessons. Now, this term is very accurate. In other words, I have not made any approximation, if you had noticed, when I wrote down this term, right. I had not made any approximation, as it is by simple calculus. For simple calculus I wrote this. I had not made any approximation there. Okay. So, at this stage let me make an approximation. Let me say that this terms uk comma I, or in other words the gradients of u is very small when compared to say 1. Okay. The gradients of strains are very small. Is that clear? So, what happens now when I say like that? What happens now? This last term here uk comma I k comma j, this last term will vanish. Is that clear? Will vanish, which means that will go to 0. Okay. Look at that, this term and this definition now. If you look at this term and this definition, it is obvious that Eij is half of ui comma j plus uj comma I plus this term. That is what is the definition, right. Is that clear? Because ds squared is this minus d capital S squared. Minus d capital X squared, I said that it is minus delta ij dxi dxj, and hence this chap and this chap go off, and hence Eij is equal to half of ui comma j plus uj comma I and plus uk comma I k comma j. Now, on top of it I have put a restriction that the strains or the gradients of u are small. We call such a situation as small strain situation. We call this situation as small strain situation, and we symbolize the strain in small strain case as epsilon ij, and epsilon ij happens to be now what? Half into I comma j plus uj comma I. But note one thing carefully, that when I said small strain, I did not say u is small. Okay, it is the gradient of u that is small. Okay, u can still be large, okay, but the gradient of u can be small, and hence in which case I can use epsilon ij is equal to half ui comma j plus uj comma I. Is that clear? Okay. Is this symmetric? So, this is a tensor. Why is that I have written half? One of the questions which students ask is, why they want to suddenly come and give 1, 2 there? Okay, why do you want to give it as half? Okay, we will come to that in a minute, because if you want to give tensorial properties to epsilon, okay, then epsilon ij has to be defined as half u I comma j plus u j comma I. Because once I give tensorial properties, you know what are the effects. I have a lot of things to say about it. Is that clear? Okay. But before that, let us see whether this is symmetric. Epsilon ij is symmetric. Obviously, from the definition itself, straight away definition itself, epsilon ji is j comma I plus I comma j. So, obviously, strain tensor is symmetric. Okay. You would think from by the way we defined, though I have been harping on this issue of the change in length quite often, you would still be thinking that what is the relationship between this and what I know from my earlier classes, right? Okay. In order to just explain that, let me take a small square. Okay. I hope it doesn't. A small square. Okay. Now, let me say that the square becomes like this, okay, where the change is say delta u1, right. Now, I am interested in say epsilon 1 1, because I have elongated the square in the 1 1 direction. Okay, this is the 1 direction. Is that clear? Okay. Now, what is epsilon 1 1 from this? What is epsilon 1 1 in this from this? Look at that, half of u 1 comma 1 plus u 1 comma 1, that means u 1 comma 1, that is dou u1 by dou x1, which is approximately from my deltas this is equal to, that is this is equal to dou u1 by dou x1, and this being a very infinitesimal thing, so that is delta x1, and hence epsilon 1 1 becomes what? Not 1. Epsilon 1 1 becomes, this is elongated to delta u1, this is delta u1. What is that? What this delta u1, this is delta u dou u1 by dou x1. So, this is u delta u. So, obviously, this is delta u1 by delta x1. What is delta u1? The difference between elongation of say 0.1 and 0.2, right. This is what we have been telling. Is that clear? Okay, this moved by u, this moved by u plus delta u. So, I just put it together, so that I say this moved by u where u is equal to 0, this moved by delta u, that is what I said, right. So, delta u1 by delta x1. So, what does it signify? Change in length by original length. So, this small strain definition still retains my first philosophy of change in length by original length. So, that is what comes out in this case. Okay, small strain case. Now, come here for a moment and look at this again. So, physically, what is this situation? What happens during this situation? Look at this. What? Physically, when will you say that it is no more small strain? What is the opposite of it? Large strain. Sometimes people call this as finite strain. Or what is the difficulty now when my strains become large? Look at this definition and look at my problem there, what I had put. No. That is not, I mean, we are talking about the issue of applying small strain or large strain. No, when this fellow becomes large, then okay, original length and the final lengths are quite different. Okay, so change in length by original length, like a simple definition may not be there. Okay, then one person can come and ask me, why do you want to say that change in length by original length? You guys may be smart. You may ask me, why not I say change in length by new length? You can immediately look at, say, nominal stress and engineering stress and so on. Is that clear? So that kind of confusion can be there, and that is not a confusion, it's a very valid point. Okay, and in order to take into account all these kind of valid points, the strain in the large deformation case is not measured by one quantity only. In other words, what I am trying to say is, one of the quantities which can, by which we can define strain, is called Green strain. Another quantity is Almansi strain and so on, and I am not going to be worried about all that right now. Okay, but nevertheless, you have to understand that the difference comes about because of the gradient of displacement. So when the gradient of displacement is small, we are not away from things what we know, and we are right there that the change in length by original length is still there. You can similarly look at a situation where delta x2 goes up, right? Okay. Now, say let us say that this is delta x1 and this is delta x2, and I am going to give a small problem for you to think for a minute. Suppose there is shear strain, I want you to remember what is shear strain, and suppose the body becomes like this. What is shear strain? Okay, gamma. This is a dx1, this is dx2. How do you define this shear strain? How do you define shear strain here? So first thing is, you have to note down what is theta 1 and what is theta 2. Is that clear? And then write down theta 1 and theta 2, and you would have defined what is called as shear strain, gamma, to be, yes, theta 1 plus theta 2. Okay. Now what is that? What is that here? No, what is theta 1? Dou u2, because this is dou u2 by approximately dou x1, okay, plus dou u1 by dou x2. Dou x1 and the original and the final lengths do not change much. That has been our small strain assumption. Though I have just put it for clarity like that, it does not mean there is so much of a change in length. Okay. So gamma, which you would have defined as dou u2 by dou x1 plus dou u1 by dou x2. Is that clear? Okay, this is how you would have defined. Now, what happens, or this is, let me call this as gamma ij or gamma 1 2, let us say gamma 1 2, to signify that we are just in the plane 1 2. Compare this with my epsilon 1 2. What is the difference there? Half. Okay. So this you have to be very careful. In fact, we have introduced deliberately a half in our definition so that epsilon becomes a strain tensor. Is that clear? Okay. Epsilon becomes a strain tensor. If not, we could have retained this. In fact, many books retain this, or many codes retain this, and it is important to find out whether you are working with gamma 1 2 or epsilon 1 2. Okay. The strain what you are looking at is whether gamma or epsilon. The difference is half. Okay. So, though we defined it very I would say tortuously, if you want to call it. Okay, I know that you have to follow really every step. I think we are not very far off from what we know. Okay, we have put that nicely down in a mathematical sense. This equation is very crucial for finite element analysis. Why? Basically because this gives me a relationship between strain on one hand and displacement on the other hand. Okay, remember, go back to our finite element days, what we did about 4 or 5 classes back. Ku is equal to F. So, what is that you are going to solve? You are going to solve for displacement. So, afterwards I have to get strain. How do you get strain displacement relationship? And what is our next step? Stress strain relationship. Let us be as rigorous as this so that all our definitions can be very nicely written down. Now you know sigma ij, you know epsilon ij, and once we complete stress strain relationship, we can get back into finite element analysis with much more confidence. We also know how to interpret results on stress. Okay? So we will enter finite element with much more confidence after we finish what we call a stress strain relationship. Okay, again we will start always from what you know, okay, and extend it in a much larger setting. Right? Okay, let us see what you know about stress strain relationship. What is that you know about stress strain relationship? What is that you know? Correct. So, what we know is sigma is equal to E epsilon. Then what else you know? There is one more term which we know, which we should use, Poisson's ratio. Okay, Poisson's ratio. So, the two things that we know is E and nu. Okay. Now, the question is that is this the way we define an elastic material? Do we say that when E is defined, okay, we define an elastic material? Because we have to set up this whole thing in a much larger canvas. Then only it will be easier for us to work out the formulations. So, which comes to a very fundamental question. This whole thing comes to a very fundamental question as to what is an elastic material. We'll worry first about elastic material and then much larger class of materials later. So, this brings us to a very important question as to what is an elastic material. Okay. So, what do you think is an elastic material? Very good. So, there are usually two definitions, as for initially also you said, and now what do you say? The first definition which students give is that stress is proportional to strain. Okay, that's first definition. The other definition, which I would say much more accurate, is that when I release the load, the shape is retained. Okay, this is a better definition. Okay, why is that this is a better definition? Because stress need not be proportional to strain. For example, if you look at rubber, stress and strain are not proportional. Okay, I can get a very complex stress strain curve, okay, where I can't define E that easily. Of course, sigma versus epsilon. Now, fortunately or unfortunately, this is not the way we define the elastic materials in solid mechanics. Okay, we have a slightly more rigorous definition. The definition comes from what is called as strain energy. Or strain energy density. Again, I am sure strain energy is not a very new term. You would have gone the other way. From stress strain curve, you would have said that strain energy is nothing but area under the curve. Okay? That is a nice way of looking at it in your earlier classes, but you would find that at this level strain energy is much more fundamental than what we call as the area under the curve. In other words, we are going to define the elastic material itself from strain energy or strain energy density function. When we say a material is an elastic material, we postulate or we say the existence of a function called strain energy density function W, which is a function of strain. We postulate, we say that if you call a material a strain energy, elastic material, then we say that the material has a strain energy density function. Okay? We will get back to what you know slowly, then you will understand what these things are. So, we postulate the existence of a strain energy density function, okay, which is a function of strains, which is a single valued function. There is only one value, single valued function, right. It is a positive definite function, single value, that means it will have only one value, positive definite, which means that it will have, for whatever be the epsilon, okay, it will have a positive value, positive definite function, single valued positive definite function. Okay. So, an elastic material is one for which I can define a strain energy density function. I can define a strain energy density function. So, that is what is very important. Okay. Now, look at that. This is W is a function of epsilon k L. Now, how am I going to define W? Okay. W, we will get back to our original thing, integral 0 to epsilon k L sigma I j d epsilon I j. This function, which I postulate that such a function exists for elastic material, is defined as W is equal to integral 0 to epsilon k L, okay, sigma I j d epsilon I j, okay, from which I can write dW to be dou W by from which I can write dW to be dou W by dou epsilon I j into d epsilon I j. Okay. And see, not from this, sorry, from this I can write like this. Okay. Now, these are the definitions of W. So, from this definition and from my dW, it is very obvious that I can write sigma I j as what? Dou W by dou epsilon I j. And this forms the basis of definition of an elastic material. We will continue this in the next class.